Welcome to Maths with Bob. Today we're looking at some polynomials and some polynomial theorems, especially the one on what's called rational roots. Now, a polynomial is obviously defined in terms of the variable x, and the coefficients belong to some sort of field. And the fields are just collections of mathematical objects. The most commonly used ones actually are the reals, R, complex numbers C, and the rational numbers Q. And you can see here they're actually Q is a subset of R, which is a subset of C. Now, basically, we can factor polynomials. The factors can be, elements of different fields, and you can see here I've actually factored px equals x squared minus 5 times x squared plus 9 over q, which is, the factors are elements of q. Then the next one there of r, because you've got some irrationals occurring. And the next one is over c, because you've got some complex numbers occurring. Okay, so that's not too bad. But this thing about rational zeros, what is a rational zero? Well, a rational zero obviously is a fractional root, if you like, or a fractional zero. P and Q are said to be relatively prime or co-prime. That is, they don't know common factors, and hence you can see here that qx minus p would be actually a factor. Now, how you actually prove this is you need to substitute in p on q for x, and you multiply everything by q to the power n in this one down here. If you actually look down, this is the one actually I multiply everything by q to the power n. I'm going to rearrange this in a minute, and I just wanted to show you what happens. Well, first up, I'll just show you. I'll try and do this with this magic pen here. Okay, that one there will actually be moved eventually over on this side, over here. Okay, as one rearrangement. And then I'll grab this term here, and I'll move this over, and over the other side. Okay, oops, doesn't want to move. Okay, over here as well, and then I'll do another rearrangement. So I call them rearrangements 1 and rearrangements 2, and you'll see in a minute we then refactor them. So if you have a look at the next slide here, you can see that the first rearrangement I've taken a factor of q out, and I've actually put, you can see here, this term over on this side, over here. Now, the next one, I've actually taken a p out, but I've actually, you can see here, that's a p taken out as a common factor, but I've actually, if you can see here, put this term here, that one there, over on the other side. Now, in the first rearrangement, you can see now that q times something is equal to minus a to the n times p to the power n, but we know that p and q are relatively prime, so q and p to the n will also be relatively prime. This basically infers that q must divide a to the n. So in fact, this number here, q, you can see here, q must go into a to the n over here. Okay, so on the secondary rearrangement, if you have a look at p must go into a to the 0 here, if you like, a0, or a to the subscript 0, or a0. Because we can't get p into q to any power, because we know p and q are co-prime or relatively prime. They have no common factors, and hence p must divide a0, okay, because it can't go into q to the power n. Okay, well, let's have a look at an example. You can see here I've got an example. Px is 5x cubed minus 7x squared plus 10x minus 14. We're told it's got one rational zero. We need to factor it over C, the complex field. Well, I've got a lot of work to do here. You can see here, we know that p must divide, okay, so the top of the fraction, if you like, must divide 14. So we have to look at the factors of 14. Wow. And then you can see here the factors of 14 are over here, okay. Oops, not terribly well drawn, but you can see here 1, 2, 7, 14. And we know that the q, which is the denominator, must go into 5, which luckily is prime, which only has, 1 and 5 as factors. And you can have a quick look there. Wow, look at all those possible zeros. Okay. As you can imagine, a fair bit of work is needed here. Okay, so after a lot of work, we find that the 7 over 5 is 0. That creates 5x minus 7 as a factor. And with a bit of long division, we can actually get a quotient of x squared plus 2. And then we can refactor that over the complex field. You can see there as 5x minus 7 is the rational root part, and then we have the complex numbers root 2i and minus root 2i, okay, as other, if you like, zeros. Okay, well, thank you for watching, and bye for now.